who's coming to us via electron from MIT. Karen grew up in Pennsylvania, a few miles and a few years distant from me. We're in Bethlehem, Pennsylvania, and she attended Barnard College. And then she went off to Cambridge for a PhD with Andy Fabian, if I remember correctly. And following that, she was awarded a Hubble postdoctoral fellowship in 2015. And then she went to the University of Maryland at their joint institute with Goddard Space Flight Center as a Garrels Fellow. And then after that, last year, she joined MIT as an assistant professor. She's done really exciting work on black holes and massive black holes. And in fact, a few months ago, I had the pleasure of spotting a quote from Erin in a news release about an AGN that flared by an enormous factor. I don't even remember. I think it was in the exponents in its luminosity change. So it obviously was a huge change in the accretion rate in a giant black hole. And you know, the timing for this talk couldn't have been better after yesterday's Nobel announcement with Gez, Genzel, and Penrose. And so this is just going to continue the excitement today. Erin is an expert on massive black holes, accretion onto black holes, accretion states, reverberation mapping, and so on. And she's doing very exciting work using several Earth orbiting X-ray telescopes. So Erin's going to talk to us today about reverberation mapping on black hole accretion flows. So with that, thanks for joining us, Erin.
Okay, thank you, Brian, for that really nice introduction. Yes,
can I just say one more thing? Erin
Sure.
has said that she does not mind interruptions. So if you would like to interrupt, let's do it the way we normally do in a talk. Just turn on your video, wave your hand, and just shout, okay?
Oh.
And she's okay with you doing that throughout the talk.
Yeah, in fact, I really actually like it because it's nice to get that feedback that you miss sometimes in these virtual talks. Okay, well, thank you for the invitation. And I really wish that I could be in Waterloo, but it's at least nice to see you virtually. So let's try and get this going. And it's, okay. All right, yes, of course, you all heard about the exciting news yesterday of the Nobel Prize in Physics awarded for the realization that Einstein's field equations aren't just, the solutions to Einstein's field equations, the Schwarzschild and Kerr metric are not just these mathematical curiosities, but actually can manifest themselves in the universe as black holes. And I love, of course, this amazing data set from the Keck telescope showing the orbits of individual stars in the center of our galaxy orbiting around some massive object that we now know is so compact that it must be most likely a supermassive black hole that is 4 million times the mass of the sun. So it's perfect timing. Today I'm going to tell you that not only do these black holes exist at the centers of nearly all, if not all, galaxies, they're not just these ornamental trinkets at the centers of galaxies. They are actually incredibly important for understanding how galaxies evolve, how our Milky Way even looks the way that it does today. And in particular, I'm going to be telling you about some of my recent work on accreting black holes with the NICER Observatory. And NICER is NASA's newest X-ray telescope. It is on the International Space Station. And there it is. You can see it moving in real time, tracking an object there with the ISS solar panels moving in the background. NICER is about the size of a washing machine. So it's very small, but it's extremely powerful. It's the largest ever soft X-ray effective area that we have, so collecting a huge number of soft X-ray counts. It has a really amazing time resolution and good energy resolution. And the thing that makes NICER really amazing for somebody who's interested in transient phenomena, is that it has this ability to slew very quickly and has flexible scheduling. So I'm going to tell you, hopefully I'll have time to tell you about two exciting recent, there's a little bit of a lag, recent work that we're doing with NICER. So I will tell you a little bit, yes, there's still a little bit of a lag. Okay. All right, so just an overview of my talk today. This is a NICER view of black hole accretion. I'm gonna start with an introduction to this technique called X-ray reverberation mapping, where we want to understand what the innermost regions around these black holes, what they look like, and yet they are too far away, too compact to actually resolve them spatially. And so what we've done is to trade spatial resolution for time resolution, and we can use these light echoes to map out the inner regions around black holes. NICER is, with its huge collecting area, is an ideal instrument for doing these reverberation studies, and I'll tell you about our work on a black hole transient that we were happy got the cover of Nature last year. And then hopefully at the end, I'll be able to tell you about this extreme black hole accretion episode that Brian hinted at that changed in 4 orders of magnitude in flux on just a few weeks time scale. But first, let's talk about, motivate why we even care about studying the inner regions around black holes. As I said, these black holes are not just trinkets, but they are important for understanding galaxy evolution. And kind of the canonical, one of the canonical ways of showing that is through this plot of the mass distribution of galaxies. You can see those points there are the galaxy mass function. And compared to the lambda CDM mass spectrum. So if, the universe was just built up and galaxies are just building up in the dark matter halos, maybe 10% of the baryons end up in these dark matter halos, then you should expect that the number of galaxies should scale, just look similar to that power law distribution of the CDM mass spectrum. But what we find when we observe these galaxies is that we're missing galaxies on the low mass side, and we're missing galaxies on the high mass side of this distribution. Now, the low mass galaxies, it seems, the escape velocity from the low mass galaxies is low enough that you can explain the lack of low mass galaxies as due to feedback from supernova explosions. So, these supernova explosions will be able to create enough energy to push out hot gas and prevent the formation of stars in these low mass galaxies. But the high mass galaxies, of course, the escape velocity in high mass galaxies is so much higher that there's not enough power from supernova explosions to explain the low luminosity of high mass galaxies and the lack of high mass galaxies. And the prevailing idea here is that AGN could be responsible for explaining that gap. Why do we think that's even possible? Well, even though the black hole is, 1,000 times less massive than the galaxy in which it resides, or even spatial scales are even more extreme, that you have something that's like the size of the black hole compared to the size of the galaxy is, 8, 10 orders of magnitude smaller. But energetically, black hole accretion is extremely important. And you can kind of see this through this little hand wavy back of the envelope calculation for a galaxy like our Milky Way galaxy with our 4 million solar mass black hole sitting at the center. So you can compare the binding energy of the galaxy using kind of typical values for our Milky Way. And you find that the binding energy is like 10 to the 52 joules. And you can compare that to the accretion energy released from, material falling into that black hole. And there, for this 4 million solar mass black hole, you get 10 to the 54 joules of energy. So the accretion power, even if it's not 100% efficiency, even if it's just the accretion power is 10%, has a 10% efficiency, still that accretion power exceeds the binding energy of the entire galaxy. So throwing stuff into a black hole has the potential to completely unbind the entire galaxy. The question, though, is how this process happens in detail. And it's thought that if there is a way to couple these the energy released from accretion to the larger scales in the galaxy, it may be able to explain kind of puzzling correlations that we see here, connecting these small scales of the black hole to larger scales in the galaxy. And the most famous of which is the M-sigma relation, that says that the mass of the black hole scales with the velocity dispersion of the bulge of the galaxy, or a proxy kind of for the mass of the galaxy. And it's thought that perhaps this coevolution between the black hole mass and the galaxy mass can be understood through this AGN feedback process, where AGN dissipate a lot of energy, release energy on very large scales. This can push the heat the ISM, and then you can't form stars, prevents the galaxy from growing through the formation of stars, and cutting off the fuel to the central black hole in this kind of feedback process. So there are kind of like two major questions when we're talking about understanding. We want to understand how this AGN feedback is possible, how it works in detail. And there are kind of two main questions that we need to answer is, how do, if you shove material into a black hole, it releases a lot of energy, it releases radiation, massive outflows, relativistic jets. How do those outflows couple to larger scales? And that is really in Brian's wheelhouse, and I will leave you to ask all of your tough questions on that to him. And the thing that I'm really interested is, but how does this how do you go from mass inflow to releasing all of the, this radiation and these relativistic jets? How is that accretion power dissipated? And really, most of the energy, most of the gravitational potential energy of that infalling material is released within, 10 gravitational radii. Tens of gravitational radii or smaller for a maximally spinning black hole, very close to the black hole. And so we really need to understand the inflow and the outflows very close to the black hole in order to understand, how this accretion process works, how this AGN feedback process works in detail. So let's talk about that inner accretion flow. This is a schematic, a zoom in of the accretion disk around a black hole. If you were to turn off all of the GR effects, all of the special and general relativistic effects around the black hole. And what you see is that material is funneling towards the black hole through this accretion disk, and it gets extremely hot. In supermassive black holes, we're talking about black body radiation that peaks in the extreme ultraviolet to maybe soft X-rays, not high energy X-ray emission above a few keV. But what we see ubiquitous kind of in all AGN is that there is this high energy X-ray emission. And in fact, high energy X-ray emission is one of the best ways to decide if a galaxy does have an accreting black hole. That's how ubiquitous this hard X-ray emission is. And the question is, where is that high energy X-ray emission coming from? Well, this is a lot of the details I'm working on, is trying to understand where that high energy emission is coming from. And it's thought to be, from this region that we call the X-ray corona. And you can see here that is this region kind of looks perhaps jet-like, very close to the black hole. It produces X-ray emission that is rapidly variable, so we know it's coming from a compact region. And the question, the basic idea is that you have some environment of mildly relativistic electrons and thermal seed photons, UV photons from the accretion disk can be inverse Compton upscattered by these mildly relativistic electrons in the corona and get upscattered to X-ray energies. And so we want to understand, okay, if we are seeing all of this X-ray emission and it's due to this inverse Compton process, that inverse Compton scattering is going to cool those electrons. So what is the heating mechanism of this corona? How does it keep staying as hot as it is, 1 billion degrees Kelvin? And here we think that the process may be akin to the corona of the sun, where you have magnetic field lines that can be twisted up due to the differential rotation of the sun and causing magnetic reconnection events that produce high energy particles. Unfortunately, in AGN coronae or in accreting black hole coronae, this process, while we think that magnetic fields must be involved in keeping this corona so hot, it's really not well understood how this process happens in detail. Even things like the geometry of this corona are still not very well understood. Perhaps it's something like a spherical region close within tens of gravitational radii of the black hole. Perhaps it's associated with the base of the relativistic jet. And these are all things that we want to understand. But basically this X-ray corona is producing this continuum of X-rays that we see from 0.1 keV up to about 100 keV. So thankfully for us, we don't have just the X-ray continuum. We have also emission line features that can help us understand these regions more. And this is can be understood through this simple schematic here, where the orange is like a cross section of the accretion disk, and the blue is this X-ray corona producing our primary continuum of X-rays. So this corona produces X-ray emission in its rest frame, is emitting isotropically. And some of those photons come to us directly. We see that as the continuum. And some of those photons will inevitably irradiate the accretion disk and cause fluorescence lines, Compton scattering off of the accretion disk, producing what we call a reflection spectrum. And this is the reflection spectrum. It's lots of atomic features, lots of fluorescence lines, Compton scattering above 10 keV. The most prominent line that we see in the reflection spectrum, this reprocessed emission off of the accretion disk, is this iron K alpha emission line. And it's, right in happens to be a place where our X-ray telescopes are most sensitive, and it's kind of an isolated part of the spectrum where there's not a lot of other atomic features. And so it has been used a lot as a diagnosis of, trying to use this iron line to understand the environments from which it came. Now, this accretion disk producing this fluorescence line is not a static disk. It is rotating. It is in the strong gravitational potential well of this black hole. And so we're not just going to see the emission line at 6.4 keV. We're going to see that it's broadened due to those Doppler shifts, those general relativistic effects. And this is an example of what would happen to one particular line. And you will add up all of these effects of the motion and the strong gravity of the black hole. So if you have a line at 6.4 keV, you will have Doppler broadening effects, just Newtonian Doppler broadening effects. And you'll have special relativistic effects. So the side of the disk that is approaching you, that emission will be beamed towards you. So the blue wing of the line will be brighter. You include general relativistic effects. So this iron line is being produced close to the black hole. And so you'll have a gravitational redshift as those photons escape the potential well. And if you add up all of those effects, what you see is this asymmetrically broadened iron line profile. And we can use that, the shape of that iron line profile to tell us what the accretion disk looks like. So you can imagine, of course, that the Doppler shift is going to be very sensitive to the inclination of the disk, for instance. And the gravitational redshift is going to be very sensitive to the spin of the black hole. So if you have a non-rotating black hole, your innermost stable circular orbit will be at 6 gravitational radii. But if you spin up that black hole, frame dragging effects will support more orbits closer to the black hole. And so you will see photons, those fluorescence lines, coming from closer to the black hole, and the gravitational redshift will therefore be greater. And so the more broadening, the stronger the red wing of that iron line, and the higher the spin of the black hole. And so this is one of the best ways that we have to measure the spin of black holes, especially for supermassive black holes. But we want to be careful about it leads to very small statistical errors, right? But we want on the spin of the black hole, but we want to make sure that our systematic errors, that we have the correct model. And thankfully, we can also use timing information. And this has been a lot of my work, is incorporating the arrival time of those photons with the spectral signatures to better understand these systems. So in a kind of very simple hand-wavy way, this schematic shows that this corona creates this power law, this X-ray continuum. Some of those photons irradiate the disk, cause the fluorescence line that we see at a later time. And just simply due to the light travel time between the X-ray continuum, the corona, and this reprocessed emission off of the accretion disk, you expect a time delay of your iron line and your reflection spectrum. So this was an idea that we knew was implicit in these models of relativistic reflection off of the accretion disk, should be that you will have these short time delays corresponding to a light travel time of a few gravitational radii. And in 2009, we discovered these reverberation time delays in an AGN 1H0707. And this is an example of another one of these systems. This is an AGN Swift J2127, and I like to show this example because it kind of shows you what we knew from the spectra and compared to what we see when we measure, incorporate the arrival time of those photons at our detector. So the figure on the left is showing the data, the spectrum, divided by some model for our continuum. And so it's not a model independent way of looking at the data, but we've taken this power law. We assume that the X-ray corona emits as a power law in this particular band. We divide out that power law, and what we're left with are these reflection features. So you can see the broad iron K line and this Compton scattering hump peaking at 20 keV. On the right is exactly the same data, now just looking at the lags and leads between different energy bands. And this is a completely model independent way of looking at the data. And what you see is that where we predict that there is an iron line and the Compton hump, we also see a time delay of those photons. And in this case, it's about 400 seconds. This is a 10 to the 7 solar mass black hole. If you did the very simple naive thing of just directly converting that time delay into a distance, you get something like 15 gravitational radii from the black hole.
Can I ask, so this lag, does it mean, like, is this measured by cross-correlating the continuum with the emission at each of these different energies? Is that what it means?
Yes. So, well, in detail, what we're doing is, for each, let's see, I think I've lost my mouse. This always happens. So yeah, take that figure on the right, the lag is a function of energy. That bin, that 3 to 4 keV is the light curve. This is the lag between the 3 to 4 keV light curve and a broad reference band. And what we do in practice is we say the broad reference band is just the entire band from 3 to 50 keV, but we remove that bin of interest so that the errors aren't correlated. And then we don't do a time domain cross-correlation analysis, we do a Fourier resolved cross-correlation analysis so that we can isolate just the highest frequency, the shortest timescale variability where we think that the reverberation, this short timescale reverberation, should be dominant. And so that's the result that you're seeing here.
And so why is it better to do this in Fourier space rather than in like a real space or time space, whatever?
Yeah, I have a really great plot, but it's not in this version of the presentation. But basically, yeah, so like in optical, you can just do a cross-correlation analysis, and the optical reverberation lags are long enough that they kind of pop out of the data. In the X-rays, if you were to do a cross-correlation analysis basically over all time scales of your light curve, you wouldn't see the reverberation signature. Instead, there's a longer time scale lag that's associated with the corona itself. This is a continuum lag that causes, it's thought to be due to like mass accretion rate fluctuations that propagate inwards and cause your high energy photons to lag behind your lower energy photons on a kind of a viscous time scale. And so that's the process that would dominate your lags if you were just to do a cross-correlation analysis. If you break it up into different Fourier modes, then you see at the highest frequencies, there is where you see the short time scale lags, this reverberation signature. Perhaps this will become clearer in a later slides. Yeah.
Okay, thanks.
Yeah, if you have a geometry of where your source is extended and of course your reflector isn't extended, you'd expect to see a spectrum of lags, right? So you're just getting a characteristic distance. Is that the idea?
Right. So yeah, we are only what this is showing is kind of the average of, if you sum up all of the response of the accretion disk, you're kind of getting some weighted average of the reverberation time scale.
Okay, yeah. Thanks.
Okay, great questions. So now we've been able to measure these reverberation lags in AGN in about 24 sources. And what we find, the figures on the right are showing the amplitude of some of these lags over black hole mass. And we find that the amplitude of the lags scales with the mass of the black hole, as you would expect if these are probing kind of regions of tens of gravitational radii close to the black hole. And recently, Will Alston had a very nice paper that showed that there is this intrinsic degeneracy between the mass of your black hole and, for instance, the height of the corona. So if you have a large black hole, you will measure longer time delays, right? And if you have a higher mass black hole, you'll also measure longer time delays. And so there was always this degeneracy between those two. And what Will found was that if you can break that degeneracy by looking at different flux observations, different states of this, of a single AGN, where perhaps the geometry is changing, but of course the mass is not changing. And if you do that, model that in detail, you can get a very tight constraint on the mass of the black hole. And this is as, this posterior is as constrained as like the optical reverberation mass measurements that we have. So this is kind of a new frontier for X-ray reverberation mapping, is not just using it to probe the geometry of these systems, but maybe as a way of getting the mass of a sample of AGN. All right, let's try to hurry up a little bit because I realize I'm pretty far along anyway. Okay, so one of the things that I've been interested in recent years is, we want to understand this causal connection between what happens when you shove material into a black hole and how, what's the effect that has. AGN are amazing, but they vary on very slow timescales, millions. The duty cycle of an AGN turning on and off is millions to billions of years. Stellar mass black holes, they are 10 to the 5, 10 to the 6 times smaller in mass, and so their variability timescales, their duty cycle is much shorter as well. And you can see an entire turning on and turning off of the black hole happening, on timescales of just a few months. And so, this is one of the things that I've gotten interested in recently, is studying these black hole transients, and in particular the low mass X-ray binaries, where you have a compact black hole in a binary system with a low mass star accreting a material, forming an accretion disk. What happens in these low mass X-ray binaries is kind of amazing, is that when you see an accretion episode, when material starts to accrete very quickly onto the black hole, they seem to follow the same trend, not just one black hole transient, but several of these black hole transients. And this is kind of depicted in this hardness intensity diagram on the bottom left, sometimes called the turtle head diagram, because it kind of looks like a turtle head. This is the X-ray luminosity versus the hardness of your spectrum. So on the right is something that is very hard, lots of high energy coronal emission from the corona. And when the black hole emerges from quiescence, on the bottom right of this hardness intensity diagram, it has a very hard spectrum. The spectrum is dominated by the corona. It increases in luminosity and suddenly transitions to becoming very thermal dominated. The accretion disk photons dominate your spectrum. And then it decays back down and transitions back into the hard state and then into quiescence again. And we know, it's kind of agreed that in the very low luminosity hard state, that your disk is going to be highly truncated, and you have this hot inner coronal flow, producing that high energy X-ray emission. And in the luminous soft state, this is where your accretion disk extends to the innermost stable circular orbit, and you're dominated by that thermal emission. And the question is, what happens in between? How does it go? How does it transition between these states? Is it dominated by an evolution of the corona, or is it dominated by an evolution of the accretion disk, and what's the interplay between these things? The other interesting connection is that at first, when you see these emerge from quiescence in the low hard state, they have a persistent relativistic jet. And as they transition to the luminous hard state, that jet turns off, and then they transition quickly to the soft state. As it transitions to the soft state, that thermal dominated state, there's sometimes a ballistic jet that's launched. Sometimes you can see those ejecta moving out. And then once it's fully in the soft state, this disk dominated state, then the jet shuts off. So there's this universal disk jet coupling that has been known for many years. And the question is now, how does the corona fit into this picture? And this is just kind of a controversial, perhaps, slide that suggests that, maybe these different accretion states in X-ray binaries correspond to different populations of AGN. And can we use what we learned from studying details of these low mass X-ray binaries to understand AGN? So I will tell you about one particular exciting black hole, Maxi J 1820, that was discovered back in March 2018 by the Maxi telescope, which is also on the International Space Station. It's an all-sky monitor. And then it triggered NICER to follow up, and we've followed it basically every day for a year. And this is what the data look like. On the left is just a light curve of this entire outburst. It was extremely bright. It became the second brightest object in the sky after SCO-X1 in X-rays. And on the right is the hardness intensity diagram here, and just color-coded in time. So you can see it emerges from quiescence in the hard state, transitions to the soft state, and back down. And what we were interested in, and yes, there was a jet that was detected, a transient jet that was detected at that jet line as it transitioned very quickly. We'll come back to that in a bit. First, let's talk about this really kind of exciting or not well understood part of the transition. We said that, okay, we agree that in the low luminosity state, the disk is largely truncated and you're just seeing this hot inner flow. And in the soft state, you're thermally dominated, the disk is extending to the ISCO. What's happening by the time you reach that hard state right before you transition to the soft state? What's happening with the geometry of the disk and the corona at that point? And this is a big question in the field because there's been a lot of controversy. Does the accretion disk, while you're in the hard state, is it, even in that luminous hard state, is the disk still highly truncated and the evolution is driven by the disk moving inwards? Or when you're in that luminous hard state, has the accretion disk already filled in to the ISCO, and what you're seeing during the transition is an evolution of the coronal geometry? So we had this amazing data set, and we said, we'll take a look with reverberation. So what we were able to do was, with this amazing data set, is to look at the timing properties. And now what I'm showing is the lag. On the right, I'm showing for the first observation, the time lag between two energy bands. The hard band here is the corona, and the soft band is this reflected emission off of the accretion disk. And what we found when we did this Fourier resolved analysis between these two light curves was this high frequency soft lag, that is the reprocessed emission lagging behind the coronal emission. This is the signature of reverberation light echoes. And we were excited because already this was a really short timescale lag, shorter than had been seen previously in X-ray binaries. And so that was telling us that we're probing closer to the black hole than before possible. But what was cool was that we were able to watch this thing evolve over a few weeks. And what we found was that the lags got shorter and shorter, moved to higher and higher temporal frequencies, shorter timescale lags. And so that tells us that something in the system is getting smaller. Either, right, in these two kind of competing pictures, either it's that the disk is moving inwards and the emitting region is getting smaller that way, or the coronal geometry is changing and the corona is becoming more compact over time. From this alone, you really can't distinguish between those two scenarios. But thankfully, NICER has this really nice, good energy resolution as well. And so we were able to track the evolution of the iron line as well. And what we found was over that same epoch, while the lags were getting shorter and shorter, the broad iron line remained very constant. And in particular, the red wing of that iron line didn't really change at all. The only thing that did seem to change was a narrow peak at 6.4 keV at the rest frame of the iron K alpha line. And that disappeared over time. So that's telling us, telling us about the geometry of this system. So putting this all together, the fact that the lags are telling us something is getting smaller, but there's no evolution in the red wing of the iron line, that means that the accretion disk is not moving inwards. Otherwise, you would see a broader and broader emission line. Instead, it must be that your coronal geometry is changing over time, that you have some constant base of this corona that is always irradiating the innermost regions, causing this broad, constant broad iron line. And yet the corona is shrinking over time, creating the shorter and shorter timescale lags.
Wait, sorry, I have a question. Okay, right. Like, so this lag you're saying, like, so this lag is measured at the highest frequency, where you see some sort of cross correlation, right? So for the other frequencies where you see significant cross correlation, do you also see the lags changing as a function of time?
You mean like at the longer timescale lags?
Yeah,
like
well,
around 2 hertz?
Yeah, sure. I mean, sure.
Yeah, I mean, you can see from this plot that that hard lag, that's that continuum lag that would dominate a time domain cross correlation. That also changes in frequency, that increases in frequency. And in fact, it may be that this is, either way, the fact that this hard lag, this continuum lag is getting, shifting to higher frequencies is also suggesting a decrease in the size of the emitting region, of the coronal emitting region.
Okay, so for all the different, frequencies where you see significant cross correlation between the continuum and a line, so for all the frequencies, you're seeing, that this lag, moves to shorter and shorter times. Is that what you're saying?
Yes.
Okay.
Yes.
I see. Okay.
Sorry, do you mind just giving a bit more intuition on what the plot on the left is actually showing? I guess what both the lag and frequency are measuring and what we should be looking at?
Yeah. So without going into too many of the details, I skipped some of the details here. But basically what we're doing, each one of these colored lines is the lag is a function of temporal frequency between 2 light curves. And in this case, it was a light curve that was like 1 to 10 keV that's dominated by the coronal emission, or 1 to 5 keV or something like that. And a lower energy light curve that's dominated by reprocessed emission off of the disk. And so the reverberation signature we would expect is that you should see a delay of this reprocessed emission. And a negative lag here is a soft band lag. That low energy, this reprocessed light curve is lagging behind the higher energy continuum. And what we're seeing is that as this evolves over time, that signature, that soft negative lag, shifts to higher and higher frequencies, shorter and shorter timescale reverberation lag. Does that help?
Yeah, thank you.
You're asking a lot of good questions about the technique itself, and I wish that I had included some more slides on that now. So, okay. We're coming to the end, and so I'll just say that now we have extended this work further with my grad student, Jingyi Wang, which he has done an amazing job now, not just looking at that luminous hard state, but actually extending this analysis to the full transition up to where you see that jet line, really the crux of everything, where it's transitioning from this hard to soft thermal dominated state. And what Jingyi discovered was that while during the hard state, we saw that something was contracting, when the source transitions to the soft state, the lags get longer again. And she has done some really nice modeling of this with general relativistic ray tracing simulations. So taking a corona and an accretion disk in the Kerr metric. What happens when you have a flash from the corona and follow those rays as they reprocess off of the disk? Can we back out, based on off of these lags, what is the height of the corona, the inclination of the disk? And what Jingyi finds is that you can see the evolution of the height of the corona, that during that luminous hard state that I was just telling you about, the corona contracts. And you can see that in the top right-hand panel. The height of the corona contracts during the hard state up to that yellow point. But as it transitions to the soft state, again, the height of the lamp of this corona increases again. And so this may be telling us something about the connection between the corona and the relativistic jet. That in the hard state, as you evolve up to this luminous hard state, that's when the radio jet, this relativistic jet, is turning off and the corona is shrinking over time. Then as you transition to the hard state, sometimes you get this transient ballistic jet. And before that jet line happens, before that ballistic jet is launched, we're seeing the corona expand again. And so perhaps this is telling us about this coupling between the corona and the relativistic jet. Okay. I think we've got like 10 minutes before the hour is up, so I would love to just stop here and take any questions that you have. If there are no questions, I can tell you about this next thing, but I'll just leave it there for the sake of time.
Keep going.
Okay, I'll be real quick with this last one. All right, so NICER is also looking at AGN, and we had a really exciting one that was actually also happened to be detected by the Assassin All-Sky in the optical on the exact same day as Maxi J 1820. So both of these extreme accretion episodes happened on the same day. This is Assassin 18EL. It is a supermassive black hole that was a quiescent galaxy, or well, it wasn't actually, I should take that back. It was not detected in the optical, but then the Assassin All-Sky survey saw a huge flare in the optical, and we followed up in X-rays. So this was an AGN to begin with, it's a local Seyfert galaxy, kind of looked like your bog standard Seyfert 1 in the X-rays, where it showed that high energy X-ray continuum from archival observations. But when we followed up, when this event happened with Assassin, NICER started taking observations, and we got some XRMM observations as well. We saw that the corona just completely disappeared by at least 2 orders of magnitude. It became undetectable in high energy X-rays. And this corona, I've said, is like pretty much ubiquitous in all of these AGN. And so to see it kind of had disappeared was surprising. All that's left over is like this thermal-like spectrum, presumably from an accretion disk. And so we thought that was pretty exciting. We were watching this thing. It became very bright in the new star band. And then it started to decay over time. And over 50 days, it became like undetectable by NICER, and it dropped in flux by like 4 orders of magnitude, which is kind of, what you might expect, but from a transient, like a tidal disruption event, that you see some large flare and then it decays over time. But we continued to watch it anyway. And what we found was that it just came back with a vengeance. And so we just kept monitoring it like every day for more than a year. And so it became the brightest AGN in the sky. It went from being like 10 to the 40 ergs per second, which is like hardly even an AGN, to becoming super Eddington AGN in just a few weeks. And as what you see on the right is the evolution of the spectrum, as the source was turning back on, the corona started to recover, and we see this high energy X-ray emission coming back. So something in this system, we're still trying to understand what could possibly have happened to, first of all, destroy a corona, and then we're now seeing it rebuild itself in real time. It's the first time we've ever seen something like this, and perhaps will help us understand how you heat a corona in the first place.
So I'm just going to parse this, if I can interrupt for a second. The red curve is labeled December 2018, but so is the green curve.
Oh, that's a typo. That's December 2019.
Okay.
Should be.
Makes more sense. Good.
Yeah. Actually, I'm not sure when the green one was taken exactly, but that's just that's a typo. Sorry.
Erin, what's the cooling time scale of the corona? If it just radiated away in X-rays and wasn't pumped?
Oh, extremely fast. Like, I don't actually. It's a good question.
I guess I'm wondering if it's longer or shorter than the decay time.
I would say shorter, but yeah, these are all numbers that still need to be worked out.
I was just wondering if this is, if you're heating it and then the heat source goes away and it just radiates and collapses.
Yeah, would that time scale make sense?
Yeah.
Brian, I'm gonna get back to you on that. It's a good question.
I noticed that the December 2018 spectrum was very steep, and then the 2011 one's very flat, and the December and June 2019 ones are more flat than that. So are you seeing do you think you're seeing evolution completely back to the original spectrum?
We're not really sure yet. We have observations that are still coming. My prediction, if my idea is correct, is that it will go back to this normal state. With NICER, unfortunately, don't have enough sensitivity at high energy X-rays. This is the figures on the right are from XMM and NuSTAR that can go to higher energies. But with NICER alone, we can't probe the really high energies. So we're waiting for observations. But what's interesting is that the luminosity is kind of now, in later time observations, is actually getting back to that archival state. So we'll have to check and wait and see if the spectrum also matches. Yeah. So the question is, how do you go? I mean, this is a change, turning on and turning off an AGN is something that should happen on time scale, the viscous time scale, millions of years. And we're seeing this happen in a matter of 100, 200 days. How does that happen? You need something that is not associated with just viscous inflow in the accretion disk. Perhaps what we're seeing is a tidal disruption event in an AGN disk, where a star comes in, disrupts the accretion disk, disrupts the magnetic field configuration required to heat the corona. So the corona is destroyed. Material floods towards the black hole because the disk has been kind of disrupted, and if material is flooding towards the black hole, that can explain this rise in luminosity again. And now what we're watching is the rebuilding of the corona in real time. So Brian's question about the cooling timescale is extremely relevant. But hopefully this can also help us understand about the heating timescale, if this turning on and reemergence of the hard X-rays is associated with, the reheating of the corona. It could help constrain these models for what produces the corona in the first place.
The energetics line up. I mean, you know how much mass there would be in a star of some mass, and you know how much power was emitted, extra power, right?
Yeah.
Or maybe it's a bigger thing because there's sort of the disruption of the star you're saying is affecting the whole accretion disk. So it's not
Yeah.
its own material.
Well, so this is actually a big question in studies of TDEs, is that the fallback rate, if you have a TDE and half of your stellar debris falls towards a 10 to the 6 solar mass black hole, that fallback rate is 2 orders of magnitude above the Eddington limit. So would totally explain, if all of that stellar debris falls into the black hole efficiently, it would totally explain the luminosities that we're seeing. In this system, as you say, it's not just the stellar debris, but there was a pre-existing accretion disk, so all of that material as well. So I think actually that doesn't seem energetically seems feasible. Yeah. That's all I had for you. And thank you for the questions throughout the talk. Helped me a lot, and I'll take any questions that you have left. Thank you.
Okay, thank you. Questions? Mike.
I know nothing about X-ray variability, so how common are these kind of, orders of magnitude fluctuations in other AGN?
Like, I've never seen anything so variable. The other thing that I forgot to mention is the gray points that you're seeing are not error bars. Those are actual data points. And like we're seeing interday variability of like 2 orders of magnitude, which is also completely unheard of. There is, recently there's been a lot of work in the optical with these so-called changing look AGN, and these are AGN that change from spectral type on timescales much faster than a viscous timescale. And this is one of those changing look AGN, but I think it's like so way extreme. Yeah.
So did people not find them in the optical until recently just because they didn't have many spectra, or, is it a selection effect by the way observations have been done, that you just haven't stared at, whether in the optical or in the X-ray, haven't stared long enough at enough things?
Right. I guess you have to go back and get multiple spectra. But yeah, Chelsea McLeod looked at the Sloan AGN and found that actually this changing look property is really common. It's like something like 20 or 30% of AGN change their broad lines on timescales that are way much too fast. So it's really like making us reconsider what we thought we knew about accretion.
Okay, that's interesting.
So I haven't thought about this just for a few minutes. It can't be cooling on that time scale. To get this kind of emission from a diffuse X-ray gas, that the time scales are going to be much, much longer. So it can't be cooling. It's got to be something else.
I would love to talk to you more about this.
Yeah, I'm out of ideas, so.
It's not obscuration.
No, it could be, but then it's 10 to the 24 or something. I mean, it'd have to be pretty optically thick to do that by obscure. Well, I don't know. It could be.
And explain 2 orders of magnitude change and fluctuate. It would have to be 10 to the 24 bricks that are.
Well, yeah, the column density would have to be, pretty big, but it may be not unheard of. I don't know. Other questions?
Sure. So you mentioned that this could be a tidal disruption event, but what about a binary black hole passing through the accretion disk and generating its own halo corona?
Yeah.
Or
you know what? I think I work on TDEs, so it's like when you have a hammer, everything's a nail. Is that the phrase? And I think maybe you work on binary. I don't know who's speaking actually. But.
Oh, sorry. This is Britt Peter. I'm a student with Avery Broderick.
Okay. Okay. Great. I mean, It could, I think it doesn't have to be a TDE. I think it has to be something that, you know, there have been hydro simulations actually that came out recently that showed this same scenario of what does it take to actually destroy a disk temporarily. And could, basically for a TDE, you have to have this sustained debris stream that has a high enough like MDOT of the debris stream, high enough densities to actually cause this destruction in the first place. And I don't know, like if a binary black hole, like going through punching through the disk, if it would do that.
Well, I know binary black holes, or a binary of a black hole that is a black hole itself, has been proposed to be the source of sort of periodic flaring in very large AGN, like OJ287, I think, which has like a 10-ish year period with a very short flaring cycle. Not at high energy X-rays, I don't think, but at other frequencies. So maybe this could be sort of a smaller scale version of that.
Yeah. Yeah, that's a good idea. I think that my explanation is not unique.
Right.
It could also just be some disk instability. We don't understand accretion disks well enough.
Well, I agree with you on that. Yeah, I mean, a lot of mysteries in AGN.
So I have a question about the jetting, and I'm trying to understand the turtle diagram by just taking standard models like you know, Blanford-Znayak and, you know, Blanford-Payne, and it seems like when you're in a high, oh gosh, I was a low hard state, you know, you might be in a Blanford-Znayak situation. When you're in a low hard, no, high soft, you might be in something closer to a Blanford-Payne kind of solution, because you've got the cool disk running into the ISCO, whereas in the other situation you may be accreting from you know, a halo. Is, you know, can you, but I wasn't sure I could convince myself from the jet phenomenology that made sense. Have you thought about it at all in that context?
I mean, what you're saying, I think, does make sense, that Blanford-Payne in this higher Eddington case where you do have a disk. And I don't know enough about the radio detections and like the spin measurements to be able to say if you only see a radio jet in like high spin black holes. Yeah. Or
I think that's still up in the air, but maybe Britt can comment on that.
Just like you said, it's still up in the air. We expect high spin black holes to be better at driving jets. But even in GRMHD simulations, being able to construct a jet has been challenging until very recently. So certainly you could have something like this. I mean, I think part of the Blanford-Payne argument is that you do have this high temperature corona above the accretion disk that sort of seeds the outflow. But yeah, this I think is still very much an open question.
Mm-hmm. But also, like in GRMHD simulations, it's also hard to get a corona in them. Yes,
I mean, I think a lot of people in Avery's group can go on for a long time about problems with GRMHD simulations, but it's one of our favorite hobby horses. But I mean, they're kind of one of the better things we have to try to tackle this stuff.
Mm-hmm.
Yeah, and I'm also making the assumption that this corona is related to the corona, you know, around a Blanford Zodiac hole, but it actually won't be immediately because that's a much hotter ordeal, right? So that, you know, the corona that would be feeding the black hole would be at vastly higher temperatures. We wouldn't see it. It radiates. It doesn't radiate in bremsstrahlung because the you know, the densities just get too low. So yeah, I don't know. I'm just, you know, meandering here, but it would be very interesting to see if one could. I mean, one of the claims from EHT was that it was consistent with the Blanford-Zodiac mechanism. Is it looks like, correct me if I'm wrong, Britt, but the spin is high and emitter is likely high. I don't think there was a good constraint on that, but
yes, we weren't able to constrain the spin in M87 really at all. But I think the assumption in all the GRMHD simulations is that any jet they form in the simulations is from the Blanford-Naik process. And so because the GRMHD simulations were broadly consistent with the data, that was the conclusion we came up with.
Well, it sounds like there's lots of work to do on this stuff. It's pretty cool. Any other questions for Erin?
Yeah, I want to follow up a little thing about the GRMHD simulations. These, as far as I know, they're done for something like a low luminosity AGN. Is this the 1E-something low luminosity when this happened?
You're talking about the AGN at the end?
Yeah, the one that flared 4 orders of magnitude.
So, I mean, it did go into this low luminosity state, but it also, you know, was large, actually like kind of hit, you see this kind of shelf around 10 to the 44. That is the Eddington limit for a 10 to the 6 solar mass black hole. And it's mostly at Eddington. And kind of interesting that it just keeps on hitting it. And
So why are you assuming it's Eddington there? Do you know what the mass of the black hole is?
we don't have good constraints on the mass of the black hole, and that is because we were seeing these broad lines change in real time. So we
Right.
really can't use those as an indicator of the mass of the black hole. But if you take the mass of the galaxy and use that as a proxy for the mass of the black hole, then you get a 10 to the 6 solar mass black hole. So it works out.
Yeah, so it's a pretty low mass galaxy then.
Mhm.
Okay.
I do know that in GRMHD simulations, people have tried to generate super Eddington outflows, and they've been able to do that just by artificially pumping up the accretion rate, which is almost cheating, right? Because if you add more gas to it, of course, it's going to get brighter. But,
And those
yeah.
also will those also form in those super Eddington GRMHD simulations. The jets are also just Blanford-Zodiac
Yes.
jets that just punch through.
Yeah.
So do you have UV observations of this? Does it have a bright UV disk?
Yeah.
Maybe I missed that. You may have said it. But
No, I skipped it. This is the UV and optical on the bottom. And so what's weird is that the UV and optical this is another reason that I think maybe it's associated with a TDE, is that it just decays kind of typical to a TDE. The spectrum, the UV spectrum, does not look like a typical TDE. But it does just continues to decay, whereas the X-rays are just doing this crazy thing.
Right, now that's, of course, the UV emission is coming from a much larger scale, right? So that's the cooler stuff from the disk way out, right? Many, like hundreds of gravitational radii.
Yeah.
So that what's going on out there could be very different, and the timescales are also very different, right? But if it is decaying, maybe whatever did, well, I don't know. The timescales are so fast there, I hesitate to guess what's going on. But this is on much larger distances, so the timescale should be. But
still did show a peak. You know, it's not that everything is happening only within
right
the innermost regions.
Yeah.
You know.
Are there any other questions for Erin? I'm sure she's getting hungry at this point. I wish we could offer you pizza, which we normally would do if you're here, but we can offer you a virtual pizza. You kind of get gypped when you give one of these talks.
It's true.
Any other questions? Okay, well, thanks so much for joining us virtually, Erin, and good luck with the rest of the year.
Thank you.